Hello everyone, welcome to lecture 19 of Mathematical Modeling and Simulation. In this lecture we are going to understand what is epidemiological model. So firstly we'll understand what is an epidemic, and then specifically we'll talk about epidemiology. Then we'll discuss classification of epidemiological models, and then we'll focus on a particular kind of epidemic model, deterministic compartmental model. And SIR is one of this kind. And then we'll also discuss few generalizations of SIR model. So let's begin. So the first question is we want to answer is what is epidemiology? And to have an answer for that, first we need to know what is an epidemic. So this is a definition coming from World Health Organization, which defines an epidemic like this. An epidemic disease is one affecting many persons at the same time and spreading from person to person in a locality where the disease is not permanently prevalent. So let's understand this. So it obviously means this is an infectious disease they are talking about because it is spreading from person to person in a locality. So that locality can be a particular city, an area, or a town, or even a whole country, and the disease is not permanently prevalent there. That means it appears due to some reason, it stays for some time and then just die out. So these depend upon how much time it stays and when does it die out. So that depends upon the disease to disease, but this is a general characteristic that it's not a permanently prevalent disease of that particular area or region. So that disease we call an epidemic, and obviously it's affecting a large number of persons at the same time. On the other hand, if you look at the definition of pandemic, so a pandemic is an epidemic spread over a large area over the whole world and continent. So essentially there is no difference between a pandemic and epidemic. The only difference is that pandemic is one kind of an epidemic which spreads its effect over the whole world. So the scale of it is much larger than an epidemic. So recently we know that this COVID-19 is declared as pandemic by WHO. So now let's move to understand what is epidemiology. The field of science that studies epidemic diseases and the factors that influence the incidence, distribution, and control of infectious diseases in human populations is called epidemiology. So it's clear from the definition that it's not only about mathematics. It's not that this is not a mathematical term. This is a very general term which includes all the broad aspects from different subjects of science and mathematics, like even the biologists who are trying to understand the structure of the virus, the mutations of the virus. So that also is included in epidemiology. The people who are trying to predict mathematically this much will be the number of infections, this much will be the point where epidemic will die out. So all that mathematics and statistics analysis, all that is also a part of epidemiology. The people who are working to create a vaccination or find a cure for it or finding a medicine for it, they are also coming in the category of epidemiologist. So it's a very broad area in which many people at the same time are working towards finding the reason of occurrence. So the influence, the incidence means how could this happen. Why they want to understand that? Because in future that can be avoided or that can be taken care of. How it is getting distributed, like person to person, what is the rate of transmission, if one person gets infected, how many other number of persons it can infect. So all those things. And most importantly, people are trying to know how to control this. So this is like creating vaccination and other things just to find a cure or treatment of that disease. So all those aspects are covered in epidemiology. And now we will be narrowing down our focus to mathematics part of it. So the mathematical modeling of epidemics is known as epidemic models, or specifically we call them also epidemiological model. So that's a tough word, or you can say it's a lengthier word. So in short, we just call them epidemic models. So here's a table showing you the various categories of models which we can use to study epidemics. Broadly, it's divided into two categories, deterministic and stochastic. So if you recall the original classification of mathematical models, so there also we had this category that some models come into the category of deterministic while others come into the category of stochastic. So even in this case, this category exists, this classification exists. In deterministic part, further we have two subcategories, discrete time and continuous time. While in stochastic, we have discrete time, continuous time, and then with discrete time, we have discrete space. With continuous time, we have discrete space and continuous space. So for understanding this, you need to know that we know that whatever mathematical model of some real world phenomena we study or formulate, because see, this is a dynamic process, it's changing every day, it's changing every minute, the data is changing every minute. So the virus is spreading its infection, the rate of transmission is different in one area, it's different in other area, or you can say the disease is traveling. So we need to understand its effect in space with respect to its position, and we also want to understand its effect with respect to time. What is the number of infections today, what's going to be the number of infections tomorrow, and so on. So the factors, the independent variables, are always space and time. So since the space and time can have both discrete values and continuous values, so depending upon that we have various combinations: discrete time, discrete space, continuous time, discrete space, continuous time and continuous space. So that just gives further classification to the model. So right now it's just for this much we need to understand. And then further we have, based upon dimension, how many factors, how many dimensions we are working in for a particular model. So according to that we can have the categories. And even in the stochastic side we have discrete time Markov chain. So what is this Markov chain? So we'll study that particularly when we'll be specifically studying stochastic models as a part of this course. So we can right now just keep it on hold. And now we'll be focusing on this side, because the model which we are going to discuss today is SIR model. So it comes under the category of a deterministic model. So let's try to understand further what is this SIR model. So these all are the various generalizations. So SIS model is also there, SIRS is there, and so on. So this just goes on because there are many number of generalizations of these models as you can explore it further. Okay, so now we are particularly focusing on deterministic model, and the deterministic way of modeling epidemic is this. We study them through a particular class of models, or you can say there's a particular name for these kind of models. We call them compartmental models. Why we call them compartmental models? This will be clear to you now. So in this, we divide the population into various classes known as compartments, where each group represents a specific stage of epidemic. So we have the whole population in the world with us. So we kind of make a virtual division that, okay, some part of the world is infected right now because you see the number of infected persons, the data. So that population is counted as infected, while some people are counted as recovered. Other people are counted as they are not even close to the infection, while some are have been exposed to the infection, like the people who have exposed to the infection, so they are quarantined. So I'm taking the example of talking all in the context of this COVID-19. So depending upon the disease, we have various compartments division, but this is the most basic division into three categories, in which we have S, I and R. We have three classes or compartments of the whole population. S stands for susceptible, I stands for infected, and R stands for recovered. So susceptible means the population which has not caught the infection yet. So it's basically like the total population which is infected and recovered is on one side, while everybody other, who has not caught the infection yet comes into the category of susceptible, because nobody is going to be like immune to this virus. They are equally, there's an equal probability of everybody catching the virus if all other conditions are same. So what I'm trying to convey is that everybody's initially is susceptible, and then slowly some people get infected. So susceptible people start shifting to the category of infected, and then with some treatment or by themselves they start to recover. So then comes a recovered category. So that's the meaning of this line, that each group represents a specific stage of epidemic. So stage means because it's running in stages. So S will go to I, will go to R. It cannot be like backwards. We cannot have infected person cannot go back to the susceptible category. Firstly, infected person will get recovered, and then probably it can go back to the susceptible category. So that part also comes in some model where we have a recovered person going back to the susceptible category. But right now in SIR, it is just this way. S goes to I goes to R. So there's a fundamental assumption which follows in all of these compartmental models, and that assumption is law of mass action holds. So basically this is, uh, okay, just read the statement and then we'll try to understand. So it states that if individuals in a population mix homogeneously, then the encounters between infected and susceptible individuals occur at a rate proportional to their respective numbers in the population. So you see now where we are going. We are now advancing towards the mathematical formulation of this model. So for that we need to talk in terms of the numbers. What is the rate of infection or what is going to happen? So this law of mass action is basically telling us that if the population is a homogeneous population, then the encounters between infected and susceptible occur at a rate. Encounters between infected and susceptible means the rate of change of a susceptible person into an infected person. Or you can say the rate of a person catching the infection, and that rate is proportional to their respective numbers in the population. So that's very obvious and easy to understand, that the more number of infected persons are there in a population, so the rate, or you can say if you try to understand it in the sense of probability, the chance of a susceptible person catching the infection is more, because more number of infected persons are there in the population. Less number of infected population is there, so less is going to be the rate of transmission. So that's what it is just saying, that this rate is proportional to their respective numbers in the population. More infected people present means more is a higher is the rate of transmission of infection. Similarly, more susceptible people are also there, so then also we have a higher rate of transmission. So that's all about law of mass action, and we are going to use it exclusively to develop the mathematical model. So this is the schematic diagram of SIR model, you can say. So this is a chain, you can say. This diagram has to be represented by this way only, as I've just told you, S to I to R. There's no other way to do that. So okay, let me just, I don't need to write it again. Okay, so what is this S representing? I've just explained to you, but I'm writing it again. S is the number of susceptible in population. So it's susceptible individuals in population at any time t. These SIR are functions of t because they are changing with respect to time. Capital I is the number of infected in population at time t, and R is the number of recovered in population at time t. So R is also a function of t. So now we'll talk about these parameters beta and gamma. So this beta is rate of transmission of the infection, or you can say It is rate at which a susceptible individual or person becomes infected, and gamma is recovery rate. So rate at which an infected person becomes recovered. So that is the recovery rate. And capital N is total population. So this should be equal to, capital N should be equal to S plus I plus R. We'll talk about it, because the total population has to be conserved. So we have just three categories of the population, S, I and R. So this total population is actually going to be equal to S plus I plus R. So this is going to remain constant, while the people will shift from S to I and I to R. So there will be interchange of the individuals from one category to another category, but their sum is going to remain constant. So let I by n be the fraction of infected individuals, because I is the number of infected individuals. If you want to calculate per unit population, that what is a fraction of individuals you are infected, so it's I by n. Then as per law of mass action, the rate of individual going from susceptible to infected class is Si by n multiplied with beta. Units of beta is per unit time. And similarly, the rate of recovery of an individual from infected class is gamma into I. Gamma units are also per unit time, the dimension of gamma. So beta and gamma both are rates. So rate means it's something per unit time. This many number are going from susceptible to infected class per day. So that's something like beta, and similarly there is a gamma. This many people are recovering each day, or so whatever. So that is gamma. So that per day or per week depend upon what you have considered, what is the unit of time you have considered for your data looking at, but otherwise it's per unit time in general. So this was to tell you that how this expression beta Si by n is coming and gamma I is coming, because see, it's beta Si by n is coming because we are not explicitly considering the I to be the total number of infected people, because what matters is one infected individuals can affect how many susceptible person to infected class. So we have to divide it with capital N to get it into the right scale, because it has to be S into I. So the number of persons into number of persons, it has to be divided with n to make it normalized. So that's why the factor is beta into Si by n. So beta is the rate of transmission from susceptible to infected class, and the units are per unit time. So that explains the rates of going from S to I. So that means this is the rate of going from S to I class. This is the rate of going from I to R class. So this is now, we are going to now formulate, write equations for SIR model without vital dynamics. So what is this vital dynamics? So we are not going to consider birth and death. See, because if you are measuring the epidemic data, or you are looking at the epidemic over decades, or over 20 years you have been investigating the data, one disease is so long, one epidemic is having its effect for such a long time that it has not died out even in 20 years. So you have to consider their birth and death, because in that much time, in that much long period of time, many people are born, a significant number of people are born, so they can affect the situation, and many people have died naturally. So vital dynamics means inclusion of birth and death into your model, while without vital dynamics means you do not just include them into your model, because if you're just studying it for a small period of time, say 1 year or some 6 months, so then it does not matter how many people have are born or died naturally in that much time. So for those kind of situation, we just apply these models without birth and death. So this is without vital dynamics. So now we are going to write the model, and so we'll be writing the differential equations because we want to see the change of the quantities with respect to time. So firstly we are writing ds by dt is equal to minus beta si by n di by dt is beta si by n, because the people who went from susceptible to infected came here, so this factor is plus here, minus gamma I. So gamma I is the number of people going from infected to recovered class, because gamma is the recovery rate. So here it is plus gamma I. So you can see this is a model, it's following the law of mass action. So the rate at which the individuals, the population of susceptibles is changing with respect to time is given by this factor, because see nobody is entering the susceptible class because we have not considered natural birth, right? We have just seen, okay, some people are going from susceptible to infected, so that's why there is just a negative term, there is just a loss term, you can say. So the how many people are going, what is the rate of their going, so it's beta si by n. So these many people are going to infected class. So obviously if this is a minus here, so here it comes with a plus sign, the same factor. And similarly from infected to recovered, these many people are going, so it's with a negative sign here. So here it is with a plus sign. That means if you add these three equations, you will get it equal to 0. So it will be ds by dt plus di by dt plus dr by dt will be equals to 0, because s plus I plus r is constant, that's not changing with respect to time. So it should be conserved on the right hand side. So this is not only true for SIR model, even if you will be studying some generalization of this model, so this has to be there. This has to be there, satisfied that the right hand side should add up to 0. This model has now this information that this left hand side is denoting the rate of change of population in one compartment or one category, you can say. So it's generally given by in minus out or gain minus loss. So this is something I've just explained you. The positive term is always the gain term. So they are coming from other category. Like here this is coming from susceptible class, while negative term is the loss term. So that's going to some other compartment. And so no loss term there is in dr by dt and no gain term is there in ds by dt, because we have not considered birth and death. So it's without birth and death inclusion. So that's why this model is, we call it without vital dynamics. So this is a model. Now we are trying to solve it. So it comes with the initial conditions. S naught is S naught, I at 0 is I naught, R at 0 is R naught. So this is at the initial time. So that's why these are the initial conditions. So remember, population growth model was also having the initial condition with that. So here we have three differential equations and three initial conditions. And this additional condition, we need to remember that S plus I plus R is equal to N. And that's because of the conservation, which I've just explained to you. So that's the complete model. Three differential equations along with three initial conditions and one extra condition, S plus I plus R equals to N. So now we'll talk about its solution. So if you look at this model, it is a nonlinear coupled system of ordinary differential equations, and no closed form solution exists. So when it was a case of population model, the logistic growth or the exponential model, or the linear growth model. So there we had just one ordinary differential equation along with one initial condition, and that differential equation was very easy to solve, so we could find the analytic solution. So those analytic solutions are also known as a closed form solution. While here you can see, although it's a very simple model, but the equations are not even linear one, they are non-linear. Where is the non-linearity? So this is the non-linearity. S multiplied with I. So non-linearity comes into picture when the dependent variables are coming as a products of each other. So it should be S square or I square, or S is multiplied with I. S, I are our unknowns, they are the dependent variables. So they are coming as a product term. So that gives this equation or the system a non-linearity. It's a coupled system. Coupled means if S is occurring here, so S is also occurring here. If I is occurring here, so I is also occurring here. So that means individually these three differential equations cannot be solved. To solve the first equation, you need to know the I value. So I will be coming from second, and third equation also will be solved if you know the solution of the second. So they are connected, they are coupled system of ordinary differential equations. So and there is no analytical solution obtained. So that only suggests that we will be solving this numerically. So we'll be talking about how to solve this kind of system of differential equations numerically. But before going to that, let's just do some analysis and try to find what is this reproduction number. So reproduction number basically tells you that how the disease is spreading. Okay, so let's just first calculate it. What is the mathematical formula for it, and then we'll talk about it. So let's focus on the second equation. The disease will be an epidemic if infection keeps on increasing. That is, di by dt is positive. So if this is positive, so obviously if the derivative is positive, means the I is going to increase, the infection keeps on increasing. So we know that if infection keep on increasing, we know that's a pandemic or epidemic. So this means positive means this factor is greater than this factor. So beta Si by n is greater than gamma I. You cancel I, so you get beta by gamma S by n is greater than 1. And we know that since S by n is less than 1, because the number of susceptibles is always going to be less than the total population, because we know of this relation S plus I plus R is n. So S by n is always less than 1. So if this factor we want to be greater than 1, so it means beta by gamma has to be greater than 1, because otherwise if beta by gamma is also less than 1, then we cannot have the product of two numbers which are both less than 1 cannot make a greater than 1 product. So if the product has to be greater than 1, that means the other number has to be greater than 1, beta by gamma. So that's the conclusion. So this number R naught beta by gamma is called the reproduction number. So it's the ratio of transmission rate and the recovery rate. So we know we have just derived the condition that the disease is going to be an epidemic if beta by gamma, that means if this R naught is greater than 1. So all the people who formulate mathematical models for epidemic, first thing they try to figure out is to calculate the reproduction number. And then based upon that, they give their prediction that if the reproduction number is going to be greater than 1, they say this is going to be an epidemic. If the reproduction number comes out to be less than 1, they say this is not going to be an epidemic, this will die out soon. So it all depends upon the reproduction number. So that's how reproduction number important quantity is, and everybody is trying to get an answer for what is the reproduction number for COVID-19 these days. And because the data is not very consistent, it's varying from country to country. So nobody so far has able to give one answer that this much is a reproduction rate or reproduction number. Sorry, it's not rate, it's actually a dimensionless number because it is the ratio of two rates. So it's dimensionless number, it's not having any units. So everybody is trying to figure out what is the reproduction number of COVID-19. They have figured out it is greater than 1, that's why it's spreading as an epidemic, but nobody is going to have so far exactly quantified it because it varies locally. For India it's different, for China it's different, and so on. It varies country to country. So that's the reproduction number. We can summarize what we have just found. that if R naught is greater than 1, beta by gamma is greater than 1, it implies disease will be an epidemic. Otherwise, if R naught is less than 1, then disease will not be an epidemic, it will die out soon. What happens if R naught is equal to 1? So that case is not right now, we are not going to discuss because that needs further analysis. But right now, that's the conclusion. So this further tells you physical meaning of R naught, which I've just explained to you. It describes the total number of secondary infections produced when one individual which is infected is introduced into a disease-free population. So this is something like we were hearing stories about this coronavirus infection, that if one COVID-19 positive person is there, then he can pass that infection to 3 persons or 10 persons, and then those further persons can pass infection to 4 persons, 5 persons, and so on. So the chain gets formed, and so that's basically the physical meaning of reproduction number. So higher the reproduction number, the faster the disease is going to spread. And now you can talk about SIR model with vital dynamics. So if you want to also include the birth and death into picture, so your model is going to be modified. So that's the meaning of vital dynamics, that if an epidemic stays for long time, it is declared as endemic. So that's another word I was talking about. And for long time, effect of birth and death needs to be included. So this will give me modified model. ds by dt will include one more term, it's the birth term, minus beta si by n, that's the old term of rate of transmission, minus mu s. di by dt is beta si by n, this is the old term, minus mu I. Minus gamma I is obviously there, minus mu I. And dr by dt is gamma I minus mu r. So we have seen the change in the model if we include birth and death. So birth term is only included in the susceptible class, because when a new individual is born, it's not directly going to the infected class or recovered class. It's assumed that the new born individual goes to the susceptible class. So this term is the birth term, and it's obviously proportional to the population. Higher the population, higher is going to be the birth rate. You understand the reproduction. Mu is death rate. It's a natural death rate. So it's occurring in the 3 cases, because a susceptible person can also die, infected person can also die, and recovered person can also die. So remember, this is not the death rate due to the disease. This is the natural death rate, right? So every person has equal probability of dying, susceptible, infected, and recovered. So this is a natural death rate mu. That's why it's same for 3 persons, whether he is infected, whether he is susceptible, whether he is recovered. The better, or you can say the improvised version of model can exist if you even include this, that okay, there is a higher chance of the infected person to die. So for the death rate of an infected person should be different than the susceptible and the recovered one. So in those kind of models, we vary the death rate for the infected. So that all depends upon how accurately or how realistically you want to model the situation. But that's the simple way of including birth and death. So it's still obviously, even it's more complicated than the previous one. So here also we cannot talk about the analytical solution. And then there are few generalizations of SIR model. SEIR. So one more category is included here, E, which stands for exposed, exposed to infection. SEIQR, where Q is stand for quarantine. So the number of people who are quarantined or isolated. SEIRS. So S goes to E, goes to I, goes to R, and recovered person again go back to the susceptible class. And we know this happens in many of the diseases, and there are many more generalizations, so you can understand that in what case a recovered can become susceptible again. Actually it becomes in every case. Even if you are having a vaccination of a flu, say we get flu shots, right? So you are not recovered, or you are not immune lifetime from that flu. You can again catch the flu over the next season, or after 5 years you have to get the vaccination again. So even the vaccinations are there, so they are never going to protect you lifetime in many of the diseases. So even if you get recovered, so there is, after some time, after you again go back to the susceptible category, you can catch the infection again. And this E stands for exposed category. That means, okay, firstly, like you can again have the example of this COVID-19. You're sitting at your home, you're just susceptible. You come out of your home and meet in with the persons, interact with more number of persons. Say you accidentally meet a person who has got the infection. So you have not got the infection yet, but you have been exposed to the infection, and then your body will take some time to show you the symptoms, and then you will come into the category of infected. Because when your test shows positive, they'll bring you into the category of infected. So that's the meaning of, that's the difference between susceptible and exposed. That exposed means person which have been in the close proximity of the infected person, so the chances of catching the infection are higher, and so on. So we can have further categories and compartments also. So all these comes under the same category. So that's all about this lecture. In the next lecture, we are going to focus on how to numerically solve SIR model. As in this lecture, I told you that we are not having any analytical solution of it, so we need to solve it numerically.